So thank you very much for wake up this early today. And so we're going to start the second lecture of Viveka on hyperbolic surfaces and curve counting. Please.
Thank you very much. And yeah, thank you everyone for coming the morning after the very nice dinner. So before I start, I just want to say I wasn't very good with this yesterday. Just give you some very brief history of this counting curves in the style of Mirzakhani. So Mirzakhani proved that recounting curves within a topological type on a hyperbolic surface, it grows asymptotically to a constant times L to the 16 minus 6 plus 2, or polynomial whose power only depends on the topology of a surface. That this was the right rate of growth was known since the 80s. Berman series and Rees independently, I think Rees maybe the lower bound and Berman series other bound, proved that coarsely there should be the growth, meaning that there's constants such that the number is bounded by the, so less than, say, C1 times L to the 16 minus 6 and greater than some constant C2 L to 16 minus 6. And in fact, they proved this for simple multicurves with integral weights. And we're going to see why this is much easier to do. I think tomorrow we will actually see a proof of why one can count those. And then I mentioned this briefly yesterday, that the first asymptotic growth was done by McShane and Riven in the case of a punctured torus and simple curves. And then came Mirzakhani's work, so proved in full generality. So first for simple multicurves of a fixed topological type in 2008, and then for any fixed topological type, so not necessarily the orbit of a simple, but orbit of any closed geodesic on any hyperbolic surface in 2016. Okay. But I do a little kind of an aside, but it's something that's going to be important later. So remember yesterday we talked about this, that if you count lattice points in just Euclidean R2, if we're in R2 and we count lattice points inside a ball in R2, say centered at the origin, our radius L, that this is asymptotic to pi times L squared. Right, it's not hard to prove, but I want to prove this in a slightly different way, because this is what we're going to do later to prove it for counting curves, namely the following way. So for each, I fix some L, and I'm going to define the following measure, ML, given by, I'm going to scale by 1 over L squared, and then I'm going to take the counting measure. I'm going to sum over all integer points in R2 and take the Dirac measure, the delta measure, centered at 1 over L times P. So what I mean here is, so if P is an integer, it's in set 2, so two integers A, B, then 1 over L P, I just mean each integer scaled by 1 over L. So this is a measure on R2. So what is this? So I have a scaling factor. Otherwise, this is a counting measure that's supported. So if L was 1, this would be supported exactly at the lattice, the integral lattice in R2. And for general L, it's like you scale the integral lattice and make it more and more dense. And in fact, if you let L go to infinity, this is the Lebesgue measure. So as L goes to infinity, this is just the Lebesgue measure in R2. And here, 2 is important for our example, but this could be done in Rn. We'd just change with 2 to n. So if you want to, you can take this as a definition of a Lebesgue measure. Okay. So why do I say this? Well, what if we evaluate these measures at the unit ball in R2? So let me write the unit ball. So in the Euclidean UE, because I'm doing hyperbolic soon, just all x in R2 of norm at most 1. So in other words, yeah, really the usual unit disk in R2. So what is ML? What is this measure evaluated at this set? Well, I have the 1 over L squared scaling. And then I get a 1 whenever 1 over LP belongs to this set. So I get number of such things. So a number of P in Z2, because that's the only way you can get if P is not an integer point, you get 0. But such that if I scale it by 1 over L, its Euclidean norm is at most 1. Right? So in other words, this is the same as saying, sorry, so maybe I'm not doing very good board work here, but this is the same as saying 1 over L squared number of integral points in Z2 such that the norm is at most L. Right? But this is the same as 1 over L squared times Z2 inside the ball in R2. Right? But we said that this measure converges to a Lebesgue measure, so this should converge to the Lebesgue measure of a unit ball. Of this set. But this is just a unit ball, so that's pi. So we get the same thing as I said over here. That is, L goes infinity, this goes asymptotically to this. Here, the L squared is just on this side instead. Does that make sense? Questions about it? So this is actually, even though this looks very simple, we're just doing lattice points in R2, this is really how we're going to prove Mirzakhani's theorem, or how we're at least going to state a different version of it. So what we're going to do, at least when it comes to simple curves, we're going to relate these things that we want to count instead to a measure that looks very much like this. It's going to be supported on, say, integral multicurves, is that what we want to count, or whatever type of curves we want to count, that's what we're going to sum over. And so P is going to be these curves. But this measure is then going to be on some space where all, so say we just consider simple, it needs to be, the measure needs to be on a space that contains all simple curves and its closure, right? Because the measure is always supported on a closure of where it's non-zero. So we need to look at the closure of simple multicurves, which happens to be exactly what's called measure laminations. So I'm going to define today what measure laminations are, and then later we're going to define the measures on those. And we're going to see that the candidate for the Lebesgue measure is what's called the Thurston measure on ML. And it actually is viewed a certain way, viewed the correct way, is a Lebesgue measure. So, okay, so that's the goal for the next today and probably tomorrow as well. But does everyone understand how these measures have something to do with being able to count something asymptotically? Okay, so we'll come back to this a couple of times at least. But let's talk about what measure laminations are. So let's go back to like our toy example of a torus. So measured or first just laminations, and then I'm going to define what measure laminations are. So if we look at the first just the actual Euclidean torus, remember that's so we have this identification of straight lines through the origin to geodesics on our torus. If it was a rational slope, we get closed loops. But what if it's not rational? So what if slope is irrational? Well, on the Euclidean torus, what happens is that you get something that's dense, right? So if you look at the quotient, R2Z2, this becomes dense. So this is dense in Euclidean torus, in the flat case. However, in the hyperbolic case, meaning if I now puncture this and put any finite area complete hyperbolic metric on it, it's not going to be dense. Very far from it's going to be nowhere dense, in fact. So it's not dense on a hyperbolic torus. Again, when I say hyperbolic torus, what I mean is that I punctured it and put a hyperbolic metric. Okay, let me give you an idea of why this is true. So the philosophy is the puncture is somewhere. This doesn't hit the puncture. And then we want to pull tight in this metric. So now I put hyperbolic metric on it, and I kind of want to take the shortest possible in this homotopy class. Okay, the pulling tight really makes sense if I have a closed curve. So let's approximate this irrational slope, say some irrational alpha, with a rational slope. Right? So let's, yeah? Sorry? Yeah, sorry. Yeah, so here I just really do the projection. And now I have this thing. It looks like this, and then, I mean, it's dense. And now I look at it on my hyperbolic torus, and I look at the geodesic representative. So really what I'm going to do, let's take some rational very close to alpha. That's going to give me a closed a homotopy class, or it's going to give me a closed loop. I look at the geodesic representative in that homotopy class, and we're going to see what that looks like, and then can approximate it better and better. So take some Qn and Q with Qn going to alpha. So each Qn gives you an alpha n closed, say, geodesic on the torus. So let's call the torus S11, one genus, one boundary component. And let's look at what these look like. So it's a general fact, a hyperbolic geometry. So I think for those of you that followed the pre-mini course, this was covered there, but I'm going to draw some pictures of why this is true. So on a hyperbolic surface, not necessarily torus, anything. There exists a compact subset such that all simple closed curves stay in that compact subset. Or geodesics. So what I mean by this, so if my surface is closed, this has nothing. So this is applies when you have cusps. So I'm saying that simple closed geodesic can't get very far into the cusp. So in the puncture torus, so now I draw it more geometrically. So we have this cusp. There is some compact subsurface, something like this, so that every simple closed geodesic lies in here. Okay. So why is this true? So if I look at this part here, this is isometric to a horoball. So I can lift it to, so there's some height here representing to where I cut this off, and then something like this. So this part here is isometric to this, to the quotient. So this is maybe, so this is maybe ht, t is the height, mod out with z goes to, say, z plus 1. We normalize this, so this is 0, this is 1. So, yeah, sorry. I'm looking here in the universal cover H2, sorry. Yeah, so that this here, the topological cylinder, is this topological cylinder where we identify these two edges. And from hyperbolic geometry, as you go higher up, these tend to each other, right? So geometrically, it looks like this, right? And now suppose I have a geodesic. It's not, let's say closed. I'll explain how we use closed. So if I have any geodesic that's in here, and it goes out here, but it's closed, so it has to come back. So I have some geodesics. So geodesics in the hyperbolic plane, right, are either vertical lines or they're half circles perpendicular to a boundary. So suppose I have something that's perpendicular to the boundary. So maybe I have something like this. Fine, no problem. But at some point, if you go high up, so you touch this thing, and you go, okay, something like this. Well, so this is a fundamental domain for this region. So if we continue this, maybe I should have done this. So I have these copies of the fundamental region. And when I put this back into here, so this goes like this, eventually it's going to self-intersect. And the higher up I go, in fact, the more intersection is going to be. And one can quantify this. One can say if you go this high up, you're going to intersect at least this many times. So what happens in the picture here is that if you go in here, you start turning around, spinning around, and then turn around, and you create self-intersections. So if you're not allowed to self-intersect, you have to stay in some compact part. So why I use closed is just that you return. So it's not, these might not project to closed ones, so they will intersect. That's fine. The only things that could escape is if you have the ones that go into the cusp. So you could have things that go straight into the cusp, but that's definitely not going to be a closed one, so it's fine. Okay. All right. So why am I saying this? So is that this kind of argument okay? No. And in fact, this is not yet simple. As long as you have a bound on the number of self-intersections, there's going to be a closed, compact subset of your surface where they all stay. So going back to here now. So suppose now this is actually a closed one, but that's approximating this irrational one very well. So it actually closed up, and we want to like pull it tight to the geodesic representative. So let me draw. Maybe I should instead put my puncture here. So here's my puncture, and I have this neighborhood that it stays away from. So they don't go. So this is what's inside here is this compact set where it has to belong. So instead of being dense, it avoids these regions, and so it looks maybe something like this. Okay, with no intersections. Right. So really, you should think of like this. This puncture is kind of like pushing it away. So what this becomes instead of being something that's dense, that like foliates the flat torus, it's instead there's some compact subset that it foliates.
So maybe you're saying there's no dense geodesics?
No. Yeah, there's no dense geodesics. In fact, we're talking about simple here, but yeah, any simple geodesic, so closed or not, is nowhere dense set. So it's very much the opposite. And it's a Hausdorff dimension 1 set. Okay, so what you get is a lamination. So I'm going to define what a lamination is, but this is like first example.
So these
yeah.
arguments that you use here works for every Riemann surface with punctures?
Yeah, exactly. So yeah, there's nothing special about the puncture torus. Whenever you have a puncture, they will always, so you can have many punctures, but if you have a simple closed geodesic, it never goes far into the punctures. It stays in some compact subset. Okay. So let me define what the measure lamination is, or lamination first. Lamination L on, let me say hyperbolic. Let me explain why I put it in parentheses. It's a compact subset yes, consisting of simple, so no self-intersections, pairwise disjoint complete geodesics. So not necessarily closed geodesics, but geodesics. So each one is simple and they're pairwise disjoint. So you can really think of it like there's a compact subset of S where it's that they foliate. Okay. So and a measure lamination. So maybe like locally it looks something like it's a bunch of. Okay. Obviously, I can't actually draw, a generic one because generically there's uncountably many leaves here. So generically, actually, if you take a cross section, it's going to be a Cantor set, generically. Doesn't have to be good. Okay, so that's a lamination. A measure lamination. Yeah.
These people do have only finitely many geodesics, or
no. So in general, there's.
But for instance, you cannot accumulate in between if the part that is opening like this.
Yeah. So I think.
I am curious about the part in between that you have.
Like here.
This D, exactly. How?
Yeah. So there's nothing. So maybe here there's a genus or something. And so this forms here a closed subset. Yeah, so like these boundary leaves are going to be dense in the thing. And yeah, so it's like accumulates onto itself, the leaves. Does that make sense? Yeah. Okay. So a measure lamination is going to be a lamination together with a transverse measure. What does it mean to have a transverse measure? It's something that gives a positive number, a measure, to every arc transverse to your lamination. And in such a way that if I homotop my arc relative to the lamination, it doesn't change. So let me write it. Measure lamination, lambda, is really a pair. I'm going to. But so L is a lamination, lambda is a transverse measure, but we're usually just going to call the whole thing lambda. So it's a lamination L together with a transverse measure. Lambda. So that is a measure assigned to each arc transverse to L. So for every arc, if I get an arc I here, I get a measure mi that is supported on I. So mi of I or mi of a sub-arc of I. And such that if I took my arc, this is I prime, it should, since they're homotopic, it should be the same, give the same measure. And the same thing, I can homotop this out like this, and it breaks into two arcs. Then the sum of these two measures should be the same as the measure assigned to this. So it acts nicely with moving the arc homotopically along the lamination. Yeah.
So this is not like a measure in this set of geodesics.
No, this is this is a measure. So you're given it always comes with a lamination, that's its support, and then it assigns measures to things transverse to arcs. Yeah.
But sorry, would you mean that for this transverse I, you have a different measure?
Yeah. So if I took
And it is automatic that you have some dependence on this measure depending on the section?
Sorry, say it again.
If you change the section, you have another method, or you are piecing only one section?
No, I can have, this goes all over my surface, right? So it's going to be different measures to each arc, but they just have to be, if it has to be invariant under homotopy relative to L. Yeah. Yeah.
The lamination in the picture is like a union of all the gamma n?
Here. Okay. So it's the limit. Okay. Yeah. Sorry. So here we just we took something very close. These were all close, right? When I say I want to pull tight, I want to think about a loop. Like it's hard to pull tight a non-closed geodesic. Yeah. So this is just something that approximates it, and so the actual lamination is the Hausdorff limit of this. Yeah. Sorry. So this approximated closer and closer and closer. Okay. Soon we're going to get a combinatorial model, train tracks for these things, and then I'm going to describe them again. But let me give you a simple example of a measure lamination, namely a simple multicurve is a measure lamination. Let me maybe introduce a notation. So ML of S is a space of all measure lamination. And here, yep.
Red is not very good too.
Oh, sorry. Sorry. So it's just saying ML of S is my notation for the space of measure laminations on S with a weak star topology on the measures.
You're not fixing the laminations for all.
For all. ML of S is all possible, yeah, exactly, all possible laminations that carry transverse measure. In fact, not every lamination will carry transverse measure, but those are two. So yesterday I made a point of having S for my topological surface, X for one with a fixed hyperbolic metric on it, and now I'm writing ML of S, but talking about geodesics. So the reason is, so actually almost everything I'm going to say is topological. In fact, we're going to rephrase also Mirzakhani's theorem in terms of measures, which is purely topological. But sometimes we need a hyperbolic metric to talk about geodesics or talk about the length or something. And the same thing is happening here, that to talk about laminations, I need to talk about geodesics, so I need a hyperbolic metric on it. But if I define this and change to another hyperbolic metric on S, I will get a space that's homeomorphic to this. So that's why we write ML of S instead of ML of X for some specific hyperbolic metric. So I really should think about it as a topological thing. Okay. But yeah, let me do a simple example, namely simple multicurves. Okay, so a simple multicurve is just so formal sum, so it's a formal union of simple closed curves. Look very close to intersecting, it's not. So maybe this, for example, is alpha, beta, gamma, and then it could have weights. So maybe our simple multicurve is capital gamma, maybe it's 2 alpha plus 1/3 beta plus gamma. Okay, this is a measure lamination. The support, the lamination, is just the union of these three simple closed curves. It is a compact subset on my surface. Yeah, and it consists of simple, complete geodesics that are pairwise disjoint. And the transverse measure is just given by the intersection number with the weights. So maybe I should have drawn one component that's a bit more complicated. Maybe this one. I don't know. Maybe this one goes. I want it to be simple. Okay, let me redraw it. Maybe it spins around this a few times. And then it goes up there. It should have no self-intersections. I just want it to be. So if I take an arc, if I take this arc, for example, then the measure assigned to that arc I of I is just, so it intersects beta once, and beta has weight 1/3. If I take an arc here, that measure is, so it intersects this 1, 2, 3, 4 times. And that was alpha, which is, had weight 2. Okay. But yeah, so generically, it's very much not a simple multicurve. So whatever generically means, but soon we're going to define a measure on this space of measure laminations, and it's generic with respect to that. So it has measure, these kind of measure laminations as measure 0. So generically not a multicurve. So like I said, the cross-section, so locally, it looks like what I was trying to draw there. So locally, you have all this, and then they maybe diverge somewhere. But a cross-section like this is a Cantor set. And the support as Hausdorff dimension 1, and is nowhere dense. However, simple multicurves are dense inside the set. So in other words, you can approximate any measure lamination with simple multicurves. So if you want, you can think of any measure lamination as a limit of simple multicurves. One doesn't even need the multi here. You just need weighted curves. So weighted simple, you take simple curves, but you're allowing any real weight on them, then it's, or rational is enough. Okay. So this is what we're going to do, like with these measures that I haven't defined yet, but it's going to look very similar to this. It's going to be measured on ML, and in at least the first instance, this integer point is going to be our simple multicurve with integral weights. Questions?
So when you say that support has dimension 1, you mean that they're very fat countersets or something?
Sorry?
You said that support has dimension 1?
Hausdorff dimension 1.
Yes.
Yeah.
So they can be very, these countersets can be very...
Sorry, a cross-section is a counter set. Yeah, sorry, I didn't write this word. If I just look at how this intersects this arc, it becomes a counter set. And if I look at the actual lamination, how much space it takes up on my surface, is as Hausdorff mentioned. Sorry, the weak star topology.
Okay.
Yeah. On the measures.
So in particular, periodic, close densities are always dense inside the object inside the lamination.
Yes, simple closed geodesics. Yeah. But you have to allow weights. You have to rescale them. But yeah. Oh, you mean the actual lamination?
The actual lamination.
Yeah. Okay. Yeah. All right. So next, I want to talk about train tracks. This is going to give us a combinatorial model to understanding measure laminations. And the goal with this is really to define a natural measure on the space of measure laminations, namely the Thurston measure. But let me first define what a train track is. Train track on our surface S, so it's the topological surface, is an embedded for us it's always going to be trivalent, but in general it doesn't have to be. Trivalent, I just mean, trivalent graph, an embedded trivalent graph. Just at every vertex there's 3 half edges that meet it, so every vertex has degree 3. Such that at every vertex, so every vertex is trivalent, but I want the 3 half edges to meet smoothly so that all 3 have the same tangent line. Such that at every vertex, the 3 half edges meet with the same tangent line. There's going to be more conditions on it, but for now, so I say half edges because these two might be the same edge. They might connect. So that locally, if you look around a vertex, it looks like this. And those that work on train tracks, usually these are called switches instead of vertices. The edges are called branches. Because really think of this as, okay, you're a train going along this track. You get to this vertex. You can choose to continue this way, or you can choose to continue this way. It's the train track switch here, which way you're going to go. But if you come from here, you have no choice. You have to continue like this, because you can't make a sharp turn like that. So in other words, at every edge, you have partitions that have, or every vertex, a partition that have edges into incoming and outgoing. Which you call which, doesn't matter. In fact, these are not going to be orientable in general, but so it gives you a way of traveling around this. Okay, together with the following condition, and such that the complementary regions so complementary regions, I mean the connected components of S take away this graph, or maybe take the metric completion of those complementary regions, are not one of the following. So you don't want a complementary region that's just a topological disk. You don't want one that's a topological monogon. You don't want a bigon. So here, I mean, there's no topology inside here. If there was a genus in here or something, that's fine. But here, like, there's nothing there. And you also don't want a cylinder. And if you have punctures, you don't want a punctured disk. So here is this green one is the puncture, my surface. You don't want this. And I think those are all. Okay. Let me draw a picture of a bigger one. But let me just say why this is natural to delete these. Because what we're going to do, we're going to think about simple closed curves, for example, multicurves. We're going to think about by following around my train track, I'm going to create simple closed curves. And I don't want to have a simple closed curve that's just homotopic to a point. That would happen here. If I had a monogon, this would mean it's not in general position. It's not in this minimum number of self-intersections, because I could just homotopy this away. The same thing if I have a bigon. I could just homotop this and put it in one. And here I don't, this is because I don't want have 2 copies of the same simple closed curve. If I do, I instead want to put weight 2 on the one of them. And here I don't want something that's homotopic into a puncture. So this is, yeah.
The problem with the n-atom with n equivalent to
So if you have a triangle, that's fine.
you have an n-atom with more
So this is a bigone. It only has 2.
Yeah, but why is it common to add another this file?
So if you have something like here, and do
What
like,
is that?
yeah, that's fine. No, this is still, sorry, what's in here is still, because so what happens if you have this, you could replace it with just one line here and then something going out. So I could homotopy this disk out. Well, if I have a bigger, if I have something like this, it's allowed, because like it continues here. And here you can't homotopy it away. Okay. So yeah, so in these pictures, this is, yeah, so how this is counted. So this might have a bunch of other vertices with things, but the complementary region is still a disk. Like, and here with this is still at 2 gone, because the corners are counted like these cusps. This is not, here you go smoothly, so it's not considered a corner. Does that make sense? So maybe draw a more complicated example. Maybe we'll have something like, maybe here's a genus, here's something else. So here's a piece of a train track. This is, I mean, it's not a topological disk, so we don't have to worry here. Did I manage to draw a bigone? Maybe this goes like this. This is now 3 gone, I think. So here are the 3 corners. That's not a corner. Okay. All right. So yeah, let's maybe do on the torus, the puncture torus. And so let me maybe put the puncture here. So here's a train track. So, and then I want to go something like this. So this is train track with 2 vertices and 3 edges. This edge is the same. So maybe this is edge A, edge A, edge B, edge B, and here's an edge C in between those. And here's another one. How do I want it? No. And that. Yeah, and sorry. This. And you can verify for yourself that the complementary region of this is a puncture 2 gone. So it looks something like this, with a puncture in there, which is allowed. Okay. Is that okay? Or did I do something wrong? I want the. Questions? Yeah.
What's the difference between the 2?
Yeah, we're going to see soon when, but imagine if you're running around this. We're going to say that this is going to represent, going to be a combinatorial model for a curve. So if I have a curve here that goes, it's going to run like along this. I'm going to explain more exactly what it means. And then comes out here, and then comes here, and then it follows this, and like this. What it's going to look like in general is a curve that goes like this. So if you want to see it as a projection of a straight line, it's going to be one whose slope is negative. This is going to represent curves that have positive slope. And that's, so there's a reason why I drew these 2. These are actually the only 2 you need to use on the torus. Okay. So a set of weights on a train track. Do I have until 5:2 or?
6 minutes.
Perfect, thank you. is an assignment of a positive number, or a non-negative, I guess, real number, WE, to each edge E. And a set of weights, so for example here, A, B, and C, if these were real, non-negative real numbers, this could be the weights. So we say they satisfy the switch equations. If at every vertex or switch we have that the weights corresponding to the two incoming sum up to the outcoming, depending on which one you call incoming or outcoming. But let me draw the picture. So if this is A, B, and maybe weight of A, weight of B, weight of C, we have to have the weight A is the sum of these two. So in our case, they're all going to be trivalents, but in general, you could have more, but it's satisfied. So in our torus, if these were weights, if A, B, and C are real numbers, non-negative, then what we get at this vertex is that A plus B has to equal C. And on this vertex, we get the same equation. A plus B has to equal C. So we only have one switch equation in this case. And in fact, so here, what the real number satisfied is, where you can take anything you want for A and B, and then C is determined. So let me relate this back to curves. Maybe some notation. So this is a set of weights. So let me say W of tau is going to be the set of solutions to the switch equations. And W sub z of tau is going to be the integral solutions to switch equations. Okay. And we're going to see that this is going to correspond exactly to, to certain measure laminations associated to tau. And these are going to correspond to the simple multicurves with integral coefficients corresponding to tau. Okay, it's going to be a one-to-one correspondence, so that's why we get the kind of a combinatorial model for these things. But first, let me define what it means for measure lamination to be carried by a train track. So measure lamination is carried by train track tau, where you usually write lambda and this thing, tau. If it supports so the underlying lamination can be homotopied into tau. So if you can move the underlying lamination first, okay, so maybe be a bit more careful. Take a little epsilon thickening of this graph and homotopy the lamination into that neighborhood, and then collapse it into the actual train track. Okay. And with some notation, so ML of tau is going to be the set of all ML in S that are carried by this train track. and ML Z is going to be all, okay, maybe I didn't give this notation, so maybe I should also give ML of Z of S is just going to be all measure laminations that are actually simple multicurves. With integral, maybe I'll give myself some space here, with integral coefficients. So remember we said in ML, an example of ML are simple multicurves. If we also restrict to simple multicurves that all the weights are integers, that's ML Z. So ML Z of tau is going to be those integral simple multicurves that are carried by our train track. Okay, so this notation. And what we're going to prove, but what I will start with next time, is that we have a bijection, in fact, with the correct topology and homeomorphism, but we just care about projection now, between all the measure laminations carried by a train track and the solutions to the switch equation of a train tracks. And if I restrict to simple multicurves, integral weights carried by my train track, it's exactly given by the integral solutions to the switch equations. So this gives us really a combinatorial model to think about it. So I'll give you at least an idea of the proof tomorrow. But really, so if these are all integers, suppose it's maybe 2 and 3 and 5. What it's going to mean is wherever you see a 2, draw 2 strands. Where you see a 3, draw 3 strands. So maybe like, so 2, 3, 2, 3, and 5, 1, 2, 3, 4, 5, if that was 3, 2, and 5. Looks like this. And there's only one, so if I'm going to create a simple closed curve, or a simple curve, particular, I'm not allowed to create any self-intersections. Exactly one way to do that. Remember, these two are the same, these are the same. So the only way you can do this is like this. And that's going to give you, in general, it could be a multi-curve, but in this case, it will give you one connected simple closed curve. Sorry, we're going to come back to this example tomorrow, and I'm going to explain that fact.